Okay, let's get started. So we're going to continue our discussion of Feynman diagrams today. Um, and as I emailed you on, messaged you on Slack, the discussion sessions are now on Tuesday and Saturday mornings and Wednesday nights. So there'll be one tonight. And you can always look up on Zoom when the next session will be. All right, so where were we? So we were looking at Feynman diagrams. So this is a very general method for just doing perturbation theory, essentially, for any many-body quantum system. So we are considering electrons with some instantaneous interaction. So if you have a general interaction of this type, some interaction V of x1 minus x2, in principle, it could also depend on the spins. Keep it very general. And then you have these creation and annihilation operators for the particle at different positions in space. Now, in Hamiltonian, all of these terms are at the same time, and so there's no explicit time written. So the way we write this interaction is this simple picture here. This is the notation for that messy expression. So the way you think about this is you think of each point as some kind of point in space-time. So this is the point x1 tau 1, and that's the point x2 tau 1, and they're at the same time in the Hamiltonian. That's why the time is the same at those points. Sorry, each vertex, that I say. Then you take a wavy line to represent the interaction. So in this case, it's an instantaneous interaction, V of x1 minus x2, which could also have some spin labels. And then we represent the field operators by arrows. So an arrow going in is a particle being annihilated, and an arrow going out is a particle being created. So at this point in space-time, particle is annihilated and created while it interacts with some other particle at this other point in space-time, which is annihilated and created. So the particle lines can carry spin indices and various other indices that the particles carry. And then the interaction can depend on everything in general. It can depend on the space-time positions, on the spins of the particles involved, whatnot. Okay. So that's the basic ingredient. And then we implement Wick's theorem by joining these lines together in some way. And in Wick's theorem, we had the basic object called a contraction. And a contraction now is just an open line. So the contraction is this bare Green's function. That's the Green's function in the zeroth order quadratic Hamiltonian of free particles. It's important that it be quadratic, otherwise this procedure, Wick's theorem, doesn't work. And we call it G0. And just notice the arrow goes from x prime tau prime to x tau, because we create a particle at x prime tau prime. So kind of going backwards, if you wish, from x prime tau prime and spin sigma prime to sigma x and tau. Okay, generally, we take the zeroth order Hamiltonian to be diagonal in spin, so a spin is preserved along this line. And the way you implement the contractions is just join all the fermions together. So if you look at the Wick's expansion that we started with, something like this, there's two different places fermion operators come in. One is from the interaction K1, which is this term here, and I've already told you how to draw them. And then there are these so-called external vertices. So those were internal vertices associated with the K1s. And then the external vertices, which is the particle you annihilated and created in the definition of G itself, because G was the time-ordered product of psi dagger. And therefore, there's one special annihilation and creation, which is not connected to an interaction, and that's called an external vertex. So that's the basic rule. You have two external vertices for this Green's function. and then everything else is an internal vertex. And then you represent the contractions by just drawing lines between them. So here's the simplest Feynman diagram. This tells you that there's a G naught directly that goes from, this is one external vertex, that's the other internal vertex, and there's a G naught that connects them. And the other two factors of G naught connect this, and so on. Okay, so this is a slightly different term, and these terms A, B, C, D, E, F correspond to various expressions we had written down in the previous slide. Okay, so now you have to do that for the denominator too. And unlike the numerator, the denominator in this expression here, the denominator is this ZG, which you can expand also similarly. That has no external vertices. So those just consist of a bunch of interaction terms which are contracted among themselves with no external vertices. So if we just apply these rules, the denominator in the Green's function over here would consist of these three terms to first order in V. Okay, now you notice a very important simple case of a very general result, which is that there's called the linked cluster theorem, that certain terms in the numerator exactly cancel those in the denominator. And the terms that cancel are what are called the disconnected diagrams. And the disconnected diagrams are exactly what the word says. They're diagrams where there are pieces that are not connected to each other. So in this case, this is a disconnected diagram. This line is not connected to anything here. This is another disconnected diagram. But this is a fully connected diagram. See, these are all the terms that appear to first order in V. Some are connected and some are disconnected. These two are connected. This is also connected. And so if I write the numerator, now when you have disconnected diagrams, because they don't involve common positions in space and time, when I'm integrating over things, there's nothing here that depends on anything there. So they're just products. I can do the integral separately on this side and this side. So disconnected diagram is just a product of the connected pieces. So therefore, I can write the disconnected diagrams like this, one free line in the numerator, times 1 plus this plus this. And then you notice that the denominator is exactly that. So then these terms will just cancel out. You only get that. And then when you expand out the denominator to first order in V, it's not going to affect these terms because these terms are already first order in V. So you don't need to worry about the product of these two. At second order, you would, but it turns out there will be a second order diagram that will cancel that out too. I'm not proving that, but you can check that. So therefore, you now get one of the first benefits of drawing pictures rather than drawing those messy expressions, that you can forget about the denominator and just only consider connected components. So this, sorry for that. Let me write it in better, more legibly. So this is just connected. So you actually never really have to worry in this same perturbation theory of any of the terms of denominator. Okay. Roughly speaking, I mean, if you think of these integrals, it's an integral over space, and you make space a finite region. What you expect of the final answer for the Green's function doesn't depend on the volume of space, because it's some local correlation function. How can it depend on how big your system is as long as your interactions are local? And the point is that the disconnected diagrams have independent integrals over space, and therefore they blow up with the size of space-time. So they better just cancel out, because otherwise the result won't be local. And that's roughly why there's this cancellation. It's quite a general phenomenon. Okay. All right, so from this, now you can get a set of rules, which I've written down here, which are also in the book. These are rules for counting various numerical factors that come in front of diagrams. Because what you notice here, for example, this diagram and this diagram, sorry, this diagram and this diagram come twice. And they have exactly the same expression, although the dummy variables of integration are slightly different. But since you're integrating them, they should be the same. So you should only evaluate one and put a factor of 2. So that's another rule in drawing diagrams. You only just draw distinct, topologically distinct diagrams, and then you use some tricks to figure out what the multiplicity of them. So there are rules for them. I can never remember them, and they vary a bit depending upon which problem you're looking at. For this particular problem with just interaction, basically, you know, I guess all those, in fact, you don't even have to worry about this because there's a 1/2 that comes in front of the term in the Hamiltonian, this 1/2. And there's a 1/n factorial that comes over here. And one of those, it turns out that for this problem anyway, the multiplicity of the diagrams exactly cancel this 1/2 and this 1/n factorial. So in fact, you just consider topologically distinct diagrams and you're done. But it's always good to check, you know, just by hand, by seeing how many ways you can contract a given picture from scratch. I always do it. It doesn't take that much time to check that there isn't any other numerical factor. So the m factorial gets canceled, the 1/2 gets canceled. And then there's the overall question of a sign. Okay, so the sign, first of all, each interaction comes with this negative sign. And then there's the sign from the Fermi exchanges that came in the Wick's theorem. And it turns out you can show that sign, that's the most difficult thing to figure out for any given diagram. What is the overall sign? Other things are quite easy, just from first principles. You just, you know, do the 1/n factorial expansion and you start doing the contraction, just counting everything. It doesn't take that much time. Getting the sign is a pain. Again, it's not difficult, but there's a rule that is very useful. Basically, the overall sign is just given by -1 to the power of number of closed fermion loops. So for example, this diagram has a closed fermion loop, so it has a minus sign. This one doesn't have any closed fermion loops here, so it doesn't have a minus sign. Okay, and these in fact turn out to be the Hartree and the Fock diagrams, and so they come with a relative sign, as we already know. Okay. And these rules are written down very clearly in the book, and I have a much better listing of them in a few minutes. Okay, the final trick before we actually start evaluating diagrams, well, a few more tricks, is a Fourier transform. So it's always good to think of diagrams in space-time because you always get them, you know, the place where you generate them is from a theory that's local in space. Meaning that, well, in this case, there's a non-local interaction, but once you go to quantum field theory, eventually everything becomes local in space in the Lagrangian or the Hamiltonian. Here, there's a Coulomb interaction that's non-local, but okay, don't worry about that. It's good to have a mental picture of, you know, Feynman diagram just being living in space-time. But then to evaluate them, space-time is a bit of a mess because you know, you have to end up taking all kinds of convolutions, and the Green's functions all depend upon the difference between 2 points. So a very useful trick is to take a Fourier transform. So you Fourier transform everything. And this is for a given diagram, that's a tedious thing. You have so many different points in space-time, the 2 external vertices, the 2 internal vertices. You have to take a Fourier transform with respect to all of them. And so just writing down the Fourier transform in the end is a bit of a mess, but in the end, the whole picture, the final result is very simple, and just state it or show you what it is for a simple diagram. So what you do is you take your Green's function, this bare contraction between 2 space-time points, and you convert it to a Green's function that lives in momentum and frequency. So this is a conventional Fourier transform, except I'm using something we're going to see explicitly in a few minutes, that the Green's function for fermions is anti-periodic in time, in imaginary time, with period 1 over temperature. And that means that the Fourier expansion in time is a Fourier series, not a Fourier integral. And the allowed frequencies are basically the related to this fact that it's anti-periodic in time with period 1 over time. That simply means that the frequencies are any odd number times pi t. And that's because e to the I omega n beta is -1. So why did we get these strange frequencies for this is the if you go forward in time, time 1 over t, which I'm now going to call beta, I to the omega n beta is equal to -1. Here beta equals 1 over temperature. And these are all the values of omega n for which that's true. So those are the allowed frequencies. These values. For bosons, it's even multiples of pi t, because they're just simply periodic. All right, so you take a Fourier transform of the Green's function. You take a Fourier transform of the interaction. So that gives you some view of Q, which we already know is 4 pi e squared over Q squared for the Coulomb interaction. And then you look at this graph, for example. So we wrote down this graph in space-time. I think that's graph, graph E. And in space-time, well, the term E is these G's with complicated space-time dependencies and different depend on space-time positions, and all of these G naughts depend on the difference of these. So we're going to use that to our advantage, the fact that these are all only depends on the difference of the space-time coordinates, and do the Fourier transform. So you have to do a lot of Fourier transforms and use the fact that a double Fourier transform gives you a delta function, and you go through all of that. So you just start with this lengthy expression, you do the Fourier transforms, and you end up with a very simple expression, which I just write down here. So now the same diagram here, which was living in space-time, now is sort of like a circuit diagram, and along each line of the diagrams, there's something like a current flowing, or they're like pipes with water flowing. And the current that's flowing in each diagram is basically the four momentum. There's a spatial momentum k and the frequency omega, and that's flowing down along. It's always oriented, even on the interaction line, even though we don't draw any arrows on the interaction line. So this line, this means that this line will give me a factor of G0 of k and omega. Okay, so it's flowing down, and then at every vertex, the current is conserved. So the net momentum coming in must equal the net momentum going out. So that's conservation of momentum, which you know is related to time translational, spatial translational symmetry. So obviously that's really why it's conserved. So here you make a choice. You say, well, let's say momentum k is coming in, and let's say the interaction line this way carries momentum q and omega. So there's no arrow on the interaction line, but you just have to give it an orientation in your mind when you write down the momentum. Just have to remember it's going this way. Okay. So if you send in momentum k and omega go this way, well, q and omega nu, this is omega n, this is omega nu, then what must be left over goes here. So that's k minus q and omega n minus omega nu. And then finally, at this vertex, again, the same Kirchhoff's law should hold, and that's automatically satisfied. If you just add these two momenta, that means that the outgoing frequency and momentum here is the same as the ingoing frequency and momentum, as it has to be, k and omega n. So this particular graph gives the contribution to the Green's function at external momentum k and omega, and is equal to g naught squared. That's this line here and this line here. And there's a G naught here, which is this G naught. And then there's a V of Q, which doesn't depend on omega. And then finally, there's a few integrations left over. And what are the leftovers? Well, basically every momentum that you had to introduce as a free variable. So in this case, I just picked some arbitrary momentum Q and arbitrary frequency omega nu. And once I made those two choices, all other momenta and all other lines were determined by conservation of momentum. So there was no other choice to make. And so these are called internal momentums, and those have to be summed over. So basically, you have some external momentum going in, you have some mess happening, and you just pick the minimal number of internal momenta you need, and the external momentum comes out is the same as the one that went in, and you then integrate over all the internal momentum. And so that's the final expression that we'll work with, and then you have to sit down and evaluate. You have to do these integrals, and then you would get the results for perturbation theory. So here's a concise summary of what I've said. The fermion lines have an orientation. So he's calling IKN instead of omega n. The interaction line comes with a minus phi of q, he calls it W of q. This is from the textbook. Observe spin and momentum, and draw all topologically different connected diagrams containing n-oriented lines, two external fermion lines, and two internal fermion lines. There's no more factors of anything, but you just as long as you make them topologically different. All vortices that contain an incoming and outgoing fermion line as well as an interaction line. Multiply each diagram by -1 to the f, in addition to that minus sign there that you have to remember. And then there's one little trick. What happened when you have, we'll see why we need it, when you have a closed fermion loop, where the two times, the initial time and the final time are the same. That turns out to be slightly singular when you have a closed fermion loop. And then you have to do what's called time splitting. You have to decide which time is ahead of the other time, which is the equal time in the interaction. So what does the time splitting mean here? Well, if you go back to the original interaction where you have the equal time size, so in this interaction, right here, so right, the times are all equal. So the time ordering symbol has no meaning on side dagger, side, side. However, we have a very definite ordering in mind when we write down this Hamiltonian in the second quantized form. Our ordering was that the size come before the side daggers. So what that means is that the size have a slightly earlier time. If you want to put it inside the time ordering symbol and remember that for this particular instantaneous interaction, the side daggers are always to the left of the size. If I want the time ordering machine to remember that, then the time ordering machine should know that actually the time on this size is slightly earlier than the times on these side daggers, so that they will always come a bit on the right of the side dagger. So that's the thing you have to remember. Now, when you evaluate the Feynman diagrams, you find that point splitting is really not important. It doesn't make any difference to the final value of a diagram, except for one diagram, which is in fact the very first diagram we're going to evaluate. And that's the diagram where you have a closed fermion loop, sometimes called a tadpole diagram, something like this. So in this tadpole diagram, these two times are the same, and you have to point split it. You just have to remember that the side dagger is a little later than the side. And this corresponds to putting a e to the I omega eta factor where eta is small and positive. Okay, so those are the rules, and it's really simple enough. It's all here. So all of the fancy stuff with time-ordered perturbation theory and Wick's theorem and the Fourier transform and the linked cluster theorem and the fermion minus sign, that's all built in to these very simple rules. Okay, so we just, now as long as you know where the rules came from, it's good to know where they came from, because sometimes you get a bit confused in the slightly more complicated problems of what the symmetry factor of a given diagram is. Then you have to just go back and evaluate it from first principles, which is generally not such a big deal. All right, any questions on the rules? Okay, so let's check ahead. So now we have this powerful technology in front of us, and we can certainly just by drawing pictures get a lot of results, and that's what we're going to do today, and hopefully finish this whole thing by by uh, Friday, and then we can start doing some new physics. And we will actually do some new physics with diagrams right away, as you'll see. All right, so let's just continue evaluating the Green's function. I showed you that there were 6 diagrams of the Green's function as first order, but no worries. Some of them canceled out, and some of them were topologically equivalent. So in terms of applying the rules at first order, there's only 2 diagrams, this one and this one. Okay, everything else is either the same as a diagram already there or disconnected. So you don't have to ever draw them. You just draw these 2 and you're done. And then you apply the rules to evaluate them. These are the only topologically distinct diagrams. Okay, so let's go to next order. So beyond first order perturbation theory. After all, that's why we developed this machinery, to do something more than first order. First order we can do a million different ways. Okay, so here are the diagrams that you get at first order, at second order. Now how many? Now these are topologically distinct and also connected. So if I had to draw everything which is topologically the same, all the diagrams I would get by doing it by brute force, so that's to be a much larger number. But if you reduce down to connected diagrams at second order, which are topologically distinct, they turn out to be already 10 diagrams. And these are the 10 diagrams. Okay, so here there's 2 wavy lines on the main line. Here's a wavy line and a tadpole. And here's them in the opposite order. Here are 2 tadpoles. And then here's a wavy line inside another wavy line. And there's a tadpole inside a wavy line. And there's a wavy line on the tadpole and a tadpole on a tadpole. Okay, it's good to have some words for them. So these are, if you just look at them, you see that in some way there's nothing really new happening here. It's just more of the same, but done more than once or inside another. And in fact, it turns out that all of these diagrams and many more are what the Hartree-Fock theory accounts for. So even if you evaluate these exactly, you will not get anything more than Hartree-Fock. Okay. However, there's 2 more, and these are really new. And this is really the first point. We're seeing something that goes beyond Hartree-Fock theory and everything we've learned so far. These 2 diagrams are quite different. This turns out, as we'll see, is sort of has some of the effects of screening built in, but not completely. And this is really genuinely a scattering diagram where particle comes in and scatters off another one, and they scatter off to completely different positions. It's just totally beyond Hartree-Fock. This also has some aspects which are beyond Hartree-Fock. Okay, so these are the only genuinely really different diagrams. Okay, so what we'd like to do is not have to worry about these diagrams, which are really more of the same, which are still topologically distinct. So there's another trick that we can now use, and that's called Dyson's equation. So what Dyson allows you to do is to even reduce further the set of diagrams to all orders, in a very simple way. Okay, so let's write down all the diagrams that we had. Well, I've only written down, these are the 2 first order diagrams, and there's 10 second order diagrams. And who knows, they go very rapidly how many third order diagrams there are. Okay, so if you look at these diagrams, yeah, this is not, there's, so what Dyson identified, I guess, I don't know if it's Dyson or not, there's something special about a certain set of diagrams. In particular, these are slightly different from any of the other ones. And these are what are called one particle irreducible. One PI is a word you'll often hear, or one particle reducible, sorry, they're not one P, they're one PR. The others are one PR irreducible. One particle So what does that mean? Well, that means so first of all, we threw out the disconnected diagrams, which is just totally different. However, in these diagrams, they're connected, but they fall apart into disconnected pieces if I cut a single Green's function line. So here, if I cut this here, it falls apart. All of these diagrams fall apart into two if I cut a single Green's function. But for the remaining 6 diagrams, they're not one particle reducible because you can try cutting any diagram, any line, it doesn't fall apart into two. Okay, it doesn't become disconnected after. So these are one particle irreducible. This is also 1 pi and 1 pi. Now the point is, with a one particle irreducible diagram, I can build a new one particle reducible diagram by just taking it twice. So, what's happening here is that the same fun is happening twice. You just have, what happened here in this region of space-time, you make it happen again. So when I go to 4th order, I could take this diagram and make another copy of it here. And really, that's true for every one particle irreducible diagram. I won't be double counting, because when I make something happen twice, I produce something that's one particle reducible. So if I start with a 1 pi diagram, I can make it happen as many times as I want and produce reducible diagrams. I can't do it with the diagram that's already reducible. Then there's the worry that you're double counting. Okay. So therefore, what I can now do is I can write my Green's function in this way. It's G0, the 0th order term, and G0 sigma G0, and G0 sigma G0 sigma G0, and sigma is the new thing. It's the self energy, or Dyson self energy. Yeah. What did I do? There was supposed to be, okay, I was supposed to hide that. Anyway, oh, I guess I say that right here, sorry. So sigma is called the self energy. Yeah, ignore the others. I'm going to explain what this omega n is later. So the fact that it was erased and it's somehow, I don't know what happened, and reappeared. So sigma is the self, let me write it anyway. Don't look at that part yet. So sigma is the self energy. And what is sigma? It's basically the set of one particle irreducible diagrams, with one more caveat, with external legs truncated, as we say. Okay, so what does that mean? So this means sigma here is this diagram, except you don't count the G naught here and you don't count the G naught here. That's what it means to truncate the external legs. So it's just this V and this G naught. This thing is only this V and this G naught, and so on. So here you truncate this leg, and that's it. Truncate that one and that one. And the reason you truncate them because they're already included here, the G naught here. So these are the external legs to begin with. Okay. And now the point of the self energy is that this Green's function series is a geometric series. It says, you can get 1 power of sigma and 2 powers of sigma, and it can happen twice. So, so this diagram here, so sigma has this, is one of the terms of sigma is this one. And now this diagram is sigma happening twice. So it's G naught, sigma, G naught, sigma, G naught. And that's exactly the term over here, G naught, sigma, G naught, sigma, G naught. And you can put any sigma you want here. In fact, sigma is the sum of all one particle reducible diagrams with external legs truncated. So finally, we have, sorry, okay. So we have reduced, so how many diagrams we had? We had, first of all, we got rid of the disconnected diagrams. Let's forget those. Then we had 2 diagrams at first order and 10 diagrams at second order. Then we said we only took out 1 particle reducible diagrams. And so then how many diagrams I've got left? Well, I had 2 diagrams at first order. And then I have, well, how many diagrams at second order that have 1 particle reducibles? That's all of these and these, so that's 6. So I have 8 diagrams. Okay, so that's so up to second order, then Dyson's trick has reduced things down to 8 diagrams. We can do even better, but before I get there, let's show you what Dyson's trick gives you then. It gives you the geometric series. And then you can, of course, we know how to sum this series. These are just products of functions of k and omega. So the sum of this series, the full Green's function, is G naught inverse minus sigma of k and omega. Okay, I haven't really told you what G naught inverse is. That is, just hold on. That's the next thing we're going to evaluate. And G naught inverse turns out to be a very simple thing. It's just I omega minus EK. And that kind of tells you why this is called a self-energy. It's like the renormalization of the energy of the particle due to the interactions. So when you're computing one Green's function, you're computing how some particle propagates through the system. And roughly speaking, the effect of the environment is simply to change the energy of the particle. Now, that's not strictly true, but that's also included in this description because the self-energy also depends on frequency. The fact that it depends on frequency in addition to the momentum encapsulates the fact that it's not really true that you can think of the environment as just changing the dispersion of the particle. I mean, that's true in the Hartree-Fock theory, but not beyond it. Yeah. Okay. So our task reduces then to just computing sigma of k and omega. And for sigma of k and omega, there are still quite a few diagrams. There's 8 diagrams. 6 here, and then 2 at first order. Okay, but there's another thing I can do. So let me just, so let me make another page on that and show you a basic result here. So there's that. So let's write them all down. So sigma is equal to, first there's this term. Let's see if I can get them all. So this, I'm going to truncate the legs. There's this term. Then there were these funny terms like this, for example. And I had also something like this. Then I had so that's 6, and then I have, as you can see, it's a lot more fun drawing these pictures than I mean, you can just imagine how many pages it would fill up if I had to write all this down in explicit form. And then I have this one. So to second order in V, these are all the terms in the self-energy. And then everything else is topologically equivalent.
So
okay.
How are the tadpoles 1 pi?
Well, if you cut them, they're still one piece. I mean, if you cut them here, they don't fall apart into 2 pieces.
But if you cut the photon propagator,
You have to cut sorry, you have to cut the particle line. I should have been more careful. Yeah,
okay.
you only cut yeah. It's the one particle reducible, so particle referring to the fermion line.
Oh, I see. Okay.
It's not photon reducible. Thank you. Okay, so these are the graphs. And it should also be evident to you that that there's something. So let's for now even ignore these two because that's generally new. But these diagrams are really not something new, because this is more of the same that you had at first order. So let me make another notation. Let me call this thing a double line. This I'm going to call as G, the full Green's function that I'm interested in. Okay. So now the full Green's function, by the previous graph, is equal to G0 inverse. Sorry, G inverse is G0 inverse minus sigma. That's Dyson's equation. That's just the sum of the geometric series. So that's this equation right here. G inverse is G0 inverse minus sigma. And that's just the sum of the series. Okay, so that's, but now let me draw in pictures. So I'm going to call G the double line. So now let me look at sigma here. What is the graph? So I'm going to propose the following expression for sigma. Let me make it a different color. So I'm going to say sigma is equal to, so this was the first term I had with the bare line, but I'm going to make it a double line. So let me make this sigma on this. And then I'll do the same for the other one, kind of interaction, and I'm going to make this line a double line. Okay, now what's that going to buy me? Well, you'll see if I take these two terms, so I make the internal Green's function not the bare line, but a full line. What's that going to buy me? Well, if I make this internal Green's function a full line, then at first order in V, when I look at the correction on the internal line, I'll precisely get this graph and this graph, because the correction at first order in V on the internal line is another wavy line, another tadpole. And similarly here, if I correct that to first order in V, I'll get a wavy line here and another tadpole. And not just that, because if I make, and now when I make the correction, there's a correction to the correction. It's really, I have done much more than include these two. I've included terms to all orders. So this, it's worth pointing that this equation it includes terms to all orders in V. And it's certainly correct to second order in V, but it keeps going. Well, sorry, it's not even fully correct to second order in V, because at second order in V, we have these additional graphs that we haven't considered. So we just throw them out for now. So this equation includes terms to all orders in V. And what is this equation equivalent to? So this is something is proven in Friedman-Velezco, I think, and maybe already, I think, proven in Bruce and Flensburg too. It's completely equivalent to something we've already been doing without drawing diagrams, the famous Hartree-Fock theory. So that's the meaning of Hartree-Fock theory, is you take the first order approximation for sigma, and so I'm going to call this sigma Hartree-Fock is equal to this. So there's an approximation to sigma. It's more than just the first order term in sigma. It's the first order term in sigma with the internal lines replaced by the full Green's function with the same approximation for sigma inside there. So it's a self-consistent equation which is exactly what you get in Hartree-Fock theory. You get a closed set of equations which are nonlinear that you have to solve. And so this is the pictorial way of writing down, just in these two pictures, writing down the Hartree-Fock equations. It's just completely equivalent to it if you try to now solve these equations in a non-translationally invariant system. I mean, as we discovered for the Jellier model, there's no big deal about the Hartree-Fock equations because the solution is just plain waves for the wave function. So there's not. So in the end, the Hartree-Fock theory becomes completely equivalent to perturbation theory, at least to first order. However, once you go to things like ferromagnetism, then there is a variational parameter to play with, and then you get more complicated set of equations. And if you want to have some fun, you can derive those equations now by just writing down the Hartree-Fock equation, where you have a different self-energy for spin up and different self-energy for spin down. And in fact, I think that should make a good homework problem in the next problem set to derive the equation for ferromagnetism from this picture. Okay. So that is what Hartree-Fock is. It's just a simple expression here for the self-energy, where the double line is the full Green's function, which includes sigma. So if you want to complete this, maybe I should have another line. Where should I sneak that in? I'll sneak it in here. Different color. So there's also this double line is G Hartree-Fock, and G Hartree-Fock inverse, like always, is equal to G naught inverse minus sigma Hartree-Fock inverse. So you have two unknowns, G Hartree-Fock and sigma Hartree-Fock, and you have two equations, and you iterate and solve them. Okay. So that's a lot of work for something we already knew about, but now we know at second order in V, there is something, a correction that's not part of Hartree-Fock theory, and that's this, these two graphs, and these are the new ones. This is beyond Hartree-Fock. And they include effects when you evaluate them, which gives the quasi-particles a lifetime. So one thing we discovered in Hartree-Fock theory, you just had a renormalized quasi-particle dispersion. If you added a particle, it lived forever and had infinitely long lifetime, but a different mass or something, different effective mass of different dispersion. But if you want to, but however, in a real system, quasi-particles don't live forever. They get scattered by other quasi-particles, and they have a finite lifetime, which will compute soon enough. And that kind of lifetime you want to compute for diagrams, you have to evaluate these diagrams, which is, not that, it takes some work to evaluate these diagrams. The pictures cannot belie all the complicated integrals that you have to evaluate these. Okay. All right, so I think that's all I have to say. Also, let's see, in this particular part. So, yeah, I mean, yeah, we'll come back to this in the next chapter. Okay, so now we have a lot of formalism, and now we have to actually use it to compute some numbers, because each diagram is actually some number, or it's a function of the momentum and frequency you're sending in general. And the basic ingredient are the contractions and the interaction V. So the one thing I haven't computed yet, I guess perhaps I should have done it earlier, is the basic contraction. What is the basic ingredient, which is G naught? So we just take, so what we have to evaluate just from first principles is you take a free electron Hamiltonian with momentum eigenstate and some arbitrary dispersion E of K, C dagger K. I have ignored spin here. So that's my H naught. So there's no V. So the time evolution of these operators, just the Heisenberg time evolution with time H naught, and we'll just put a hat to remind you of that. So this is what G naught is defined to be. It's the expectation value in the free Hamiltonian H naught of the time ordered product minus C times C dagger. Okay. So now we just have to turn the crank and evaluate everything in here by, basically simple harmonic oscillator type physics, but for fermions. So the first thing you want to evaluate is the interaction representing the imaginary time of Ck with this Hamiltonian. So this you can evaluate many ways. You can write down a differential equation for the left and the right-hand side, or you can note it, and that equation is basically the same equation in a harmonic oscillator. And in a harmonic oscillator, you know that A of t is A of A times e to the minus I omega t. Here, because you're in imaginary time, you don't get the I, and the omega is replaced by the energy. So this is the basic time evolution of Ck, is e to the minus Ekt tau. Similarly, you can take the time evolution of C dagger of tau, and it gives you e to the plus Ek tau times C dagger. Okay, and please note, and this is quite important, that despite the notation, this operator is not the Hermitian conjugate of that operator. Because if I take the Hermitian conjugate of this, I will get, since this is a real number, I will get e to the minus Ek tau here. Of course, this is the Hermitian conjugate of this for real physical time, because then there's an I here, and that will change the sign, the exponential. But for imaginary time, that sign is not there. And so you have to be a little careful in writing down time evolutions and just remembering this fact. Okay. All right, so now we just plug this in here. So first we take care of the time ordering symbol. The time ordering symbol tells us when theta is big, when tau is bigger than tau prime, then you get C dagger. And when tau prime is bigger than tau, I get C dagger C. And these are all in the interaction representation if I want to be consistent. Okay, now I can use these time evolutions that I've just evaluated. That gives you this exponential decay, which is common, which I can pull it out. And then finally, I have to just evaluate the equal time expectation value. C dagger C is just the number operator. So this is just the number of fermions at temperature T. And that's, of course, given by the Fermi function. So here, the function have absorbed the chemical potential inside the definition of Ek. So NF of Z is equal to 1 over e to the beta Z plus 1. That's the Fermi function. So this gives me the number of fermions in the state with energy E. So that's NF of Ek. And this, by the fermion anti-commutation relation, is 1 plus C dagger, 1 minus C dagger C. So that gives me 1 minus NF of Ek. Okay, so that's our final result. Nothing very easy to remember. So G naught of T, the basic ingredient in the Feynman graph expansion, is this object here. Every line has this factor. And really, the whole point of diagrams would be defeated if you have to draw this, write this complicated term every time we had a line. Looks like a mess. But the Fourier transform comes to the rescue. So the first thing you notice, which is something I promised, it only depends on tau minus tau prime. I mean, there are all these theta functions, but the final answer only depends on time differences. All right, so we can just set one of the times to 0, with put time tau prime equal to 0. So it's C of tau with C dagger at tau prime equals 0. So that, okay, that makes it a little more simpler to write down with tau prime equals 0. And now it's very useful to now remember the KMS condition. So the KMS condition was that for negative time, G of tau at negative time was related to G of tau at positive time by a sign. Okay, so let's take tau less than 0. So we fix tau less than 0. If tau is less than 0, then only this term contributes. And that's just equal to the Fermi function, the minus signs cancel, times e to the minus ek tau. Simple enough. Now with tau less than 0, compute tau plus beta. We want to check this anti-periodic property. So if we compute it, then this term will contribute. So you'll get 1 minus nf of ek. And now the time tau is tau plus beta. So that's tau plus beta. Now, 1 minus nf, if you just compute from that, is e to the beta ek or e to the beta ek plus 1 times this. And lo and behold, this term is exactly the negative of that. Just simple algebra, you can check that's the case. And so it's happening from a very, very cute trick here. The beta in the denominator is crucial for that to work. So the fact that the Fermi function involves exponentials of energies over temperature, and the time evolution involves exponentials of energy times time, then the time 1 over temperature is very special, and that's why the antiperiodicity appears. Okay, so this is an antiperiodic function, at least in this fundamental domain. And so now we take the Fourier, we only need to integrate in the final graphs the fundamental domain. So therefore, because we're taking a Fourier series, so yeah, I've already, so these frequencies are omega 2n plus 1 pi t, sometimes called the Matsubara frequencies. I think I have to stop. Okay, so then I'll just take the result and we'll just, of course, go over it again. So now you take the Fourier series representation. So this is how you invert between tau and omega, the usual Fourier tricks. And now given this g of tau, you can go ahead and evaluate the Fourier transform by doing the integral. Again, it looks like a huge mess, but lo and behold, at the end of the day, it's very, very simple. This is the propagator of the fermion with frequency omega and energy E. It's just 1 over omega minus E. This is an imaginary frequency, that's why there's an I here, and that's it. So the propagator of a particle in frequency space is just 1 over the frequency minus the energy. That's kind of a universal structure in many Green's functions, even in quantum field theory. This appears here in imaginary time and at an arbitrary temperature. Okay, so now once you have this, now we can pull out our diagrams and evaluate them quite easily. At least the simple ones. Okay, thank you. All right, so I'll stop there, and happy to have a discussion tonight at 9 p.m. Or if there are any questions now, I'm happy to answer them too.
I have a couple questions. So
yeah, go ahead, Jonah.
Would you be able to explain just a little bit more physically what this KMS periodicity condition means? Like why exactly do we have that we're sort of periodic or anti-periodic on this domain?
Yeah, it goes back to the original definition of the Green's function. Maybe, let's see. Yeah, so this is a very general definition of the Green's function here. So what you notice is that, yeah, I didn't go through the proof, but you have two different types of exponentials of Hamiltonians here. One is the time evolution of A of tau and B of tau prime. It comes in with different factors of U. So A of tau and B of tau prime have this time evolution, which is given here.
Mm-hmm.
But this e to the minus beta h also is like a time evolution of time beta. And then I didn't quite show you the intermediate steps. You can combine all the different time evolutions inside the time ordering symbol and just one basic time ordering. Okay, but now suppose I had reversed the, suppose I now take the same thing and move tau to tau plus beta. And I'll get slightly other time is appearing here. And it turns out you can then use the periodicity of the trace. You can take operators around in a trace without any trouble, because that's the property of the trace, the fact it's making a trace. And you can use the periodicity of the trace so that to show quite generally that the function has to be either periodic or anti-periodic in time beta. I guess it becomes a little more clear in path integral language. So in path integral language, you have this evaluating trace of e to the minus beta h. In the path integral language, that just means you're taking path integral on a time that runs from 0 to beta, which is a circle. And therefore, so any correlation function on a path integral on a circle has to be periodic or anti-periodic. For the partition function, it's always periodic. For Green's functions, because you're taking a Fermi operator around, it becomes anti-periodic.
But I guess
go ahead.
Well, I guess just physically, why are we evaluating things sort of, at the same time? Why are we not allowing evolution from one time to the next that is not periodic?
Well, this is all in imaginary time. If I'm actually computing a physical Green's function for a physical experiment or a scattering experiment or photo emission or something like that, then I do have to go to real time. Right now, you should just view this as some tricks I'm playing with the imaginary time Green's function.
I see.
These are definitely different times, tau and tau prime. The only place we had the same time was in the Hamiltonian itself. And that's because we just had an instantaneous Coulomb interaction. That's in the condensed matter context, we have an instantaneous Coulomb interaction because the velocity of light is much larger than the velocity of any electron. So we can just take it instantaneous. In reality, even that is not instantaneous. They do have different times. You have to put a photon and so on. So we want to avoid those complexities, and that's why we have an instantaneous interaction. But in the Green's function, these are definitely different times. I put tau prime equal to 0. I didn't put tau prime equal to tau.
Right.
And that's just simply using time translational symmetry.
Right. Okay, and that sort of brings me to my next question, which is, so we're working with a non-relativistic Hamiltonian. So in these Feynman diagrams, are the particle, do they respect Lorentz invariance, and are the particles allowed to be off shell, or is it different because we're working with this particle?
Okay, so first of all, yeah, we are working. So in principle, this is very, very general, either relativistic or non-relativistic, because I didn't tell you what EK was. EK can be anything. Or a Galilean invariant system is k squared over 2m, but it could be anything. It could even be square root of k squared plus m squared. So an example of a relativistic system in condensed matter would be graphene, okay, where you have a relativistic dispersion. So what is really different about relativistic system is that you have both particles and antiparticles. That's the approximation I made. I'm only keeping the particles. So in graphene, it's sort of like keeping the top of the Dirac cone, but not the bottom of the Dirac cone, which is filled. Now, if I had a semiconductor, that's fine if I'm in the conduction band. I mean, a semiconductor is a better analogy to relativistic QED, where the electron is massive. So I have a valence band and a conduction band, the other way around, a valence band and a conduction band. And I'm only looking at, say, that's the conduction band. And the valence band is full. But if I include excitations in the bottom band down here, which would be holes, those would be the positrons, and they would have negative energy if I want to use this formulation. So I could equally well use this for relativistic particles, but I would have to put negative energy for the antiparticles, and the same formalism would go through. I would have to put a bound there in the end. Now, what you do in quantum field theory is you cleverly take some combination of the particles and hole in a way that's the whole formalism relativistically invariant,
right?
And you don't have to worry about the negative energy states. this is just a different way of doing the bookkeeping. It gives you the same answers in the end. And certainly everything is off shell. I mean, in the off shell language would correspond to the delta function where the frequency is equal to EK. Here, the frequency is not constrained to be equal to EK. So in some sense, we are including off shell effects.
Mm-hmm.
Off shell here in the more elementary language is the statement that, there's a compare what happens when you do perturbation theory for an energy eigenstate. You get all these energy denominators, which are non-zero, and you sum over all intermediate states. Those are states that are off shell. On the other hand, when you do something like Fermi's golden rule, you only have delta functions on the energies. The energy must be conserved because you're looking at some time-dependent process with some initial state and a final state after a long time. So that's the on-shell process. And that also comes in Green's function by taking the imaginary part. So the Green's function can compute both things. They can compute the off-shell effects, which is the shifts in energies. So the quasi-particle mass is not the same as the bare mass. That's computed by these diagrams effectively by off-shell effects. It's the same as first and second order perturbation theory. And then has on-shell effects like lifetime of particles, which we haven't really considered yet.
Mm-hmm.
That's all in there. But it just comes from just taking the real and imaginary part of the Green's function. I guess when we looked at the particle hole continuum and we do this plasmon pole, that was an off-shell part. And we're going to get the plasmon pole next lecture using diagrams.
Okay, thank you.
Sure. Okay, great. So happy to continue this discussion tonight, unless there's a pressing question right now. Okay, then.